and we take it from there. All right, so one common theme which came up in Madhir's first question, what is lattice? So if you think about it, all the crystals and many of the crystals are, we use them in everyday life. Sodium chloride is a crystal, right? So, and they are bound with ionic bonds. So the idea is that sodium chloride, so it's a long range, it's infinite 3D kind of a structure of what we call as crystal, right? And now when you think of an infinite 3D, infinite, of course, it's finite, the crystal grain stops somewhere, but if I'm an atom and I'm sitting there and I look around this a huge network of sodium chloride, sodium chloride, sodium chloride, sodium, for me, it's infinite, right? Now, how do I, if we are dealing with it and we want to say maybe calculate forces between sodium and its 4 neighboring chlorides, how would I do that? 6 neighboring chlorides. Sorry, if you see the red one here, that's sodium, the green one is chloride. So the red one is connected to 6 other, right? So for the green one also. For that one red atom, it's an infinite network on all 3 dimensions. Okay. Now, for us, when we treat it, we don't want to treat the infinite network of all those things. So we say, okay, and the whole thing, we call it a lattice. So lattice is nothing but repetitive coming of the same thing over and over. I say, okay, let's take just one of those things, which would represent the whole thing, right? So you should think about it. We can pick one, maybe set of 6 atoms or maybe 8. I don't know. Depends on which crystal you're looking at. Or in this case, we can just take one cube. And rest assured that one cube, we can deal with that. We can calculate everything we want to deal with it. And rest assured, that's the same thing which will be repeated over and over, right? With me? That's the basic idea of a crystal and lattice and why we want to do with this. Because today we'll get into a little bit more depth on what do we want to do with it. Now, the sodium chloride is an ionic salt, right? It's not semiconductor material, but it's a crystal. So we talk about crystals. So crystals, yeah, there's no Breaking Bad reference in this course, okay? So we just talk about sodium chloride and we'll talk about semiconductor materials, no other crystals. But nevertheless, they all, the things are what? Ordered structure of atoms. And for sodium chloride, you put it in water and the ionic bonds are so weak, the water replaces and dissolves it, right? So you get ionic liquid. But you cannot do that with silicon. So yeah, so there are other crystals that would not dissolve, that are hard solids. So, but the treatment of crystal in solid form is almost the same. So now when you talk about atomic arrangement, so think about carbon. So carbon comes in many forms. Carbon comes in the form of, can you give me an example of carbon, how it comes in nature?
Like elemental carbon or
Yeah, carbon, just carbon, elemental carbon.
graphite, I think.
Graphite, right? So graphite is what? In our pencil, a cheap material, we have it on our pencil, the pencil tip. How else do you find carbon?
Diamonds.
Pardon?
Diamonds.
Diamonds, right? Now this is black carbon, which we write, and it's cheap, worthless. And diamond is a shiny object, which is transparent, gives you colors of light, and so expensive. What's the difference?
The structure.
Atomic arrangement. That's the title of this slide. So atomic structure, atomic arrangement. So when we put them all together in a random order, they are nothing but cheap graphite or coal, right? We do barbecue, so we burn coal. That's also carbon. But when the atoms become well ordered, they become crystal, that totally changes carbon and becomes the hardest material in the world. There are other hardest also. So now but we have to deal with crystal because crystalline structures are what we use in semiconductor materials. So we define these things. So periodicity or repetition and that symmetry is what we call the letters. And now we say, okay, we pick the simplest lattice point and we say, okay, that's the basis. And from which we find, okay, what are the things around so we can pick them up and we say, okay, they repeat over and over. So we call that as the unit cell. So unit cell may not be the basis because we that was the discussion as the last lecture I posted that the most simplest one may be difficult to deal in geometry. So we may choose a bigger one, which may be easy to handle, right? So then the bigger one is what we'll call as unit cell, right? So now if you think about crystalline structures, this is an amazing example where we see silicon in well-ordered silicon atoms in a precise order for infinite length or area. Of course, we would make things smaller so we can manage, but if we want to, we can make the crystal infinite if we can handle it. But for then treatment of unit cell or the atomic arrangement, then we have to look at small pieces. And then from those small pieces, we say, okay, how are they connected to each other? So now sodium chloride was a crystal, but not a semiconductor material. It was not a metal. It is a metal in chemistry form, but it was not a hard material, right? You can easily break it. But when we get to things like silicon, germanium, or other hard materials, so these atoms are very tightly bound with each other in a precise order. On the right hand side, if you see they all packed together, you don't see an order, right? Because it seems jumbled up atoms, but no, there is a precision there, which is visible from the top of this figure where you see these atoms are lined up and all that. So from that, then we can pick up a bunch of basic atoms and we say, okay, that's uh, can be taken as a unit cell. We did this discussion last time in a lecture, which was we had a phase cubic. Well, we had a simple cubic, a cube where there's an atom on every corner, and there was a homework question on that. So I hope you have gone a little bit in depth, but we'll touch that upon as well today. And then if you take that, so you have a cube, you have to deal with cube, you have to use basic concepts of geometry, right? So every corner has an atom. And if it's a BCC, then if it's FCC, what was FCC? Does somebody remember what was FCC? I talked about simple cubic. Does anybody remember what was FCC?
Phase center cubic.
Phase-centered cubic. All right. So in which every phase has one atom. And then there was another thing called BCC.
Body-centered cubic.
Body-centered cubic, right? So these are simple structures. And then we can count how many atoms would be there in one phase, maybe, or the whole volume as well, right? So we've done that. But now another problem comes in. Okay, so we have identified a unit cell, and we have identified where are all those atoms located. But still, how do I orient myself if I'm one atom sitting in a corner? How do I make sense? And this will become clear why I give this example that I'm an atom and I'm looking at other atoms, because I have to share my electrons. It's going to become an electron device. So I have to know where are others located. So I strategically put myself in this corner today because we'll be talking about a room as an example of a cube. So if there was an atom in that corner, it has to know where is the nearest atom. Is it in that corner or is it in that corner? you can visualize my room as a cube, right? Or if there is an atom on the other corner at the bottom, which one is the closest one? Because guess what? I have to share electrons with them to become a conductor or a semiconducting device. So we have to then come up with a way of identifying planes and directions. So I put down a cube on a 3D Cartesian coordinates, right? We all know Cartesian coordinates, X, Y, Z, right? So I put it down there. Now I say on, and I say, okay, this is the size A. What do we denote A as when we talk about unit cells? What is small a? A apple.
Is it the length?
A, we call its length, we call it lattice constant.
Oh, okay, yeah.
You guys have to remember these things. Lattice constant. What is lattice constant? What is the significance of lattice constant? Lattice constant is the distance between two atoms that we use to define a unit cell. It's measured. We know exactly precise distance. I've shown you a picture where we can actually see atoms. So we can measure how far those atoms are. We measure them in angstroms. Angstroms is 1/10 of a nanometer. You have heard nanotechnology. Some of you may have taken course with me on nanotechnology. So nano is 10 raised to the power minus 9. Angstrom is 10th of that. It's 10 raised to the power minus 10. So we know precisely what is the unit length. Sorry, unit cells dimensions, because we have lattice constant. Now this A is, I put A to show lattice constant. So we take a cube. Now I say each face of that cube is unique because it's going in different direction. Yeah, I read in your discussion board, you said you had to go back to basic chemistry, right? High school chemistry. I'm going to take you to basic geometry today as well. I'm sorry, but the beauty of devices is this, it's all high school level of science. So if you stay with me, things will make sense. So, okay, a plane. What is the direction of a plane?
The normal.
50?
If I take a plane, what is the direction of a plane?
Like outward of it.
A normal angle.
Normal, perpendicular to the plane, right? Fantastic. So that's fundamental geometry. Any plane, when we talk about direction of a plane, we always talk about the vector. That's vector. Started talking about vector also. I'm bringing physics in here as well. So why, we'll see why. Again, that atom sitting in that corner needs to know which direction can I share my electrons to become a conductive device. Every atom is important. So we say there are three, this fundamental basic example, we say define three crystal planes. I'm using the word crystal planes, very important word. You have to remember this, crystal planes. It's symmetric, but we still have to make sense of a plane, because in every plane there may be different number of atoms. You have done this homework assignment where you had to count how many atoms were there, right? So that's important, because if you do conductivity in one plane which has more atoms than another plane that have less atoms, the conductivity would be different. The charge travel would be different. So that's why it's important today for us to know early on. All right. So we identify the set of planes or direction, right? We plane, it has direction. And we call them by three set of integers. We say HCl. This system was developed by a scientist. Can you guess what was his name? Dr. Miller indices. You'll see people call it Miller indices, Miller indices. Yeah, Miller indices. Now, what do? We define what we have done is we say, okay, there is an algorithm we use to calculate or find out what is the plane. We use 3 numbers to define a plane. So so this algorithm is saying something here. So just stay with me. Think about blue plane. If you pick blue plane, you can see that the intersect with X. What is that point? The X intersect. It is intersecting at A, right? But for that point, the Y and Z are infinite because it never interacts, it never intersects Y and Z at all, right? So we can call that point A infinity infinity. That's what it says here. Now, number 2, blue plane intercept X is at A 0, 0. Oh, sorry, we'll flip it next step so it becomes infinity. Let me put some annotation so we know we all are talking about the same thing. So if I pick this point, what are its coordinates? A 0, 0. If I pick this point, what are its coordinates? 0, A 0, right? If I pick this point, what are its coordinates? And I see this point is part of this plane, this blue plane. This guy is part of this plane, the yellow plane. And this guy is part of this plane. So if I find this any point on this plane, that would be telling me all about the orientation of this plane. Now, what is the 0? It's just an arbitrary. You can put your thing anywhere on that crystal, but once we put it, then we define everything in terms of that that origin. All right, what's the next step? So, and this is why we are doing. I'll come back to this one later on, but let me just walk you through Miller indices. There's some videos also I'll post in this, so you'll get a little bit more understanding of that. Now, Miller indices, what do? They give us 3 HKL, 3 numbers, which tells us exactly in 3D space what is the location of one plane, then the other plane, right? So you can see 2 planes behind me. And if we do that, then you can find distance between 2 planes also, again, basic geometry. D equals a formula which can tell you the distance between 2 planes. You can also find angle between 2 planes as well, right? Now, why is that important? Because going to this idea, let's pick the difficult one. So if I was looking at this front face, let me change my pen. If I was looking at this front face, or if I was looking at this face, that's also a plane, right? You guys follow that if I can chop it at an angle, that's also a plane. But if I take the front facade, which is, let me change color, which would be this, that's also a plane. But the number of atoms in these 2 planes are different. Okay, let me state it in terms of density. That's much more easy to compare. The density of atoms in plane shown by red square and the rectangle showed by pink color, the density of atoms is different. You may not be seeing that right now, so trust me on that for now. It will become clear as we go along. If the density of atom is different, then the charge contribution will be different. If you have more atoms in one plane, that plane will be more conductive than if you have a plane which has less atoms, right? So atoms have to share their charge carriers. Are you with me so far? Yes, no. I only see
That
William.
makes sense.
Only William gives me a clear yes.
Yes, we're still here.
Because if you understand why we are doing this, we are soon be calculating those planes themselves. And it's a simple way of how we do that. But we have it's something new. You haven't seen that before, so we'll have to learn that. So there's the first step. We find the intercept. The second step is we invert that intercept. We do it 1 over that intercept. And what we do is once we do that 1 over that thing, then we have to multiply with the common denominator. Let me take a step back. I've gone too fast here. So the number 3 here, we find the intercept like we have done here. Sorry, here, right? A00, 0A0 or 00A. Then we flip them. We say, okay, 1 over A, 1 over 0, 1 over 0 for the blue one. But then we reduce them to their smallest value while retaining the relationship with them. So then if you have 1 over A, you have to multiply everything with A to bring it back, right? So then we'll do this example. And what we end up is we identify there are numerous combinations for those planes, and I'm giving you a little bit more examples now. It's not just the face of the cube that matters. We may be looking at an intersection going through, cutting the cube into half diagonally or maybe vertically, or we may be looking at something that makes a triangle with 3 corners. All of them have their own Miller indices, and these are written here. For the blue one, it's 001. If it's the top, for the front one is 010. The side is 1 bar 00 because we are, instead of taking the front one, we are taking the back one. So they are symmetrical. All right, let's look at this example. So this comes straight from the book, figure 1-5. You guys want to take a look at the book at this stage? If you bring up 1.5, 1-5, I bring up 1-5, we can look at the thing and it'll be slightly easier for us to go through that. All right. Do you have it up? Example 1 dash, it's 1-2. Oh, yeah, it's figure 1-5, example 1-2. Have it up? Let me share my screen so we can, I can share you from my screen. That's much easier. So what's the process? Let me make it larger. So, okay, they gave us a plane. They said, okay, this is the plane. Find the, what do you call it? The plane coordinates, right? So what is the Miller indices of the plane? Here are 3 steps given. We find the intercept, take the reciprocal of those, and then reduce it to the smallest number of integers, which is shown here. So we got the plane, and first step we said, okay, let's find out the intercept. For the x-axis, what's the intercept? 2, right? For the y, what is the intercept? Yes, 1, 2, 3, and 4. I say 4. For Z, what's the intercept? 1, right? And then they say flip it. So I say 1 over 2, 1 over 4, and 1 over 1. Now, we have to reduce it. So we simplify this number. What should we multiply it with?
4.
4, right? So I say multiply with 4. So what do we get? We get 2, 1, 4. That is the plane. This plane is 214. That's what's written here also. Are you with me on the step? If I give you a plane on a Cartesian coordinate, can you find the Miller indices for that plane?
Sir, do you care if we go like XYZ or XZY or?
Always XYZ.
Okay.
Always XYZ. All right. So what we have done today is I can tell you. So we have seen a basic unit cell. And today I've told you if you are given a crystalline plane, you can find what are its Miller indices. Why does it matter? Because Miller indices will tell you in the next step what can be the current density, because you will know atomic density in that plane. You'll be amazed. We know exactly how many atoms are there in a unit cell. If you know that, then we know exactly how many atoms are there in a semiconductor chip, right? Because we know the density, we know the area, we can find out exactly how many atoms would be there. We count atoms. All right, so we are together on this Miller indices. All right, let's go back to our slide and the more things there. The more examples and few more, little bit more practice on that. So we walk that through. Now, if you know one side, anything that's at 90 degree is an equivalent plane. So instead of writing one plane, we can just write all the equivalent planes in one writing. So here, for example, 0, 1, 0, 1, 0, 0, zeros, they're all equivalent to each other because they're all the same size. They carry the same number of atoms in them. So instead of writing all of them, we can just write maybe one of them, but we instead of using the brackets, what do you call this thing? We call these curly braces. Instead of using the small round ones, we use curly braces. So curly braces just tell us that it has a number of bunch of equivalent planes that go with that. Let me go back, right? So yeah, so we even further simplify. Instead of writing each one, we can write a few of them. And all the equivalent ones are covered with those curly braces. All right, so if you now look at a crystal unit cell, again, they can be, I can't say gazillions of them, but there are so many crystal planes that one can identify from one unit cell, right? Because that would help me when I make a wafer, silicon chip, I can order a wafer that has 100 plane on it, or 001 plane on it, or 111 plane on it. And my need for how many atoms I need or how many electrons I need would dictate what plane do I order from manufacturer. Does that make sense? why we are doing this exercise, right? So now, soon this will happen when I will talk about 100 plane and you will know what does that mean. So moving forward from module 2, you guys will need to know uh, what are those planes. There's a message in chat by Julio Camacho, which is for you guys. So it's between you guys. Don't bring me into that discussion in the chat. And there's Luis Juarez also gave a message. As instructor record, I direct you to the bookstore to buy the book. So these are your friends who are sending you chat messages. All right, with me on this? Guys, I talk your language. Don't think that I'm sitting on the other side. It's to help you guys. Take a look at that. Now, we talk about sodium chloride. We talk about imaginary cubes, simple cube. They're not imaginary yet. There are so many materials that have that structure. But what about semiconductor materials? So silicon, germanium, carbon, they have what we call as diamond lattice. So like symbol cubic, FCC, BCC, there is a diamond lattice also. So we don't use the word diamond like we use diamond in everyday life with that expensive thing you have to give your fancy to ask her to marry you. No, not that diamond. This is just, we call this structure as diamond lattice. And they are built up. So we have a diamond structure, I'll show you right now, but then there may be slight changes or slight special things about which would be basically a diamond structure, but there'll be few changes in that, going from one to the other. And the one example is where all the atoms are not of the same material, but they have different materials. Like in sodium chloride, we have sodium and chloride, which make an ionic bond, right? So they are ionically, chemically attached to it. But we may just bring two elements together and we mix them, but they don't do chemical reaction with each other. What do we call that kind of material? When you mix two material, they don't chemically react, but they homogeneously become part of the whole structure. What do we call that kind of metals?
Mixture.
I use that word mixture, but there's a special name for those kind of mixtures.
Homogeneous mixture.
Take a step back. You're in the wrong direction. So yes, they make homogeneous mixtures, but they are solids. We call them alloys, right? You have heard the word alloys, right? So what is an alloy? Again, it's two or more materials mixed together that do not react, but they're homogeneously mixed. One step further, in this, they would be making a crystalline structure, which means every atom has a precise location where it's supposed to go. It cannot be randomly spread out, right? So that's where we say, if you say the second bullet point, that would help you understand. In many compound structures, atoms are arranged in a basic diamond structure, but are different on alternating sites, right? So if you have gallium arsenide, for example, GaAs, we call it gas also, right? Gallium arsenide would have gallium arsenide, gallium arsenide, gallium arsenide, but they are not making ionic bonds like sodium chloride. That we are done with sodium chloride example now. We are talking about now hard material, semiconductor material. So if that happens, we call that special shape of diamond to be, we call it zinc blend structure. Just 2-3 names you have to remember: diamond structure and zinc blend structure, which is a special structure of diamond structure. But in this case, we have alternating elements. And this is typical of 3,5 compounds. So when we mix 3 and 5 compounds together, you guys know what is 3 compounds, 4 compounds, and 5 compounds. Where does which group silicon belongs to?
4.
Group 4. We say group 4. That's the word we use. Group 3, group 4, group 5. Very good. So now, okay, how does it look? Then I'll come back to this slide. First, let me show you how does the structure of diamond look. So what we have done here is, if you take the FCC, I hope you all know what is FCC by now. I want to know who does not know what does FCC mean in this room. Show me your thumb if you don't know what is FCC. Because if you don't know, then you're going to be lost going forward. Okay. Show of hand if you don't know what is FCC. So if you know what is FCC, then we are adding another twist to the structure. We are placing 4 more atoms to FCC. And the thing is, they are being placed at another precise location, which is 1/4. Sorry, this I went in the wrong direction, which is 1/4 to corner and 1/4 up. So from every atom, this is 2 vectors. So if you do these 2 vectors, you add them, what is your result? Sum. This is your resultant vector. So that's somewhere in the air, not at the face. So this was face, this was corner, and then there was center. No, these are 1/4 moved away from every atom. So what we are showing here is we have just picked some atoms. We have shown the distance 1/4, but trust me, all these black ones are 1/4 from every other atom. So if I were using this, I would still see that this was 1/4 by 1/4 by 1/4 atom away. So precisely it's 1/4 this direction, 1/4 in this direction, and 1/4 in this direction. All right. So what's the twist in diamond structure? There are 4 more atoms in it on top of FCC. Now I go back to my previous slide and show, we talk about that bullet point I missed there. I skipped there. So what does a diamond structure mean? It is an FCC lattice with an extra atom placed at every A quarter vector, B quarter vector, C quarter. Basically in X direction, go 1/4 of lattice constant. In Y direction, go 1/4 of lattice constant. Again, can somebody remind what is lattice constant?
How far away the atoms are from each other?
So no. So lattice constant is the size of a unit cell, 1 dimension of the unit cell. Unit cell is a cube, but 1 direction is lattice constant. And of course, X is A, Y is A, Z is A. So what we are doing is we are taking 1/4 of lattice constant. What are the units for lattice constant?
Angstrom.
Angstrom, right? 1/10 of an nanometer. So we are doing is we are going, okay, it is lattice constant that's dividing 4. We are writing these vectors just to show that you are going in X, Y, and Z directions. So what essentially we are getting today is we are looking at the the lattice constant or the crystalline structure of silicon, which is diamond structure, right? Not the diamond lattice, not the diamond lattice, right? Which is FCC with 4 more atoms which are placed 1 by 4, 1 by 4, 1 by 4 in each atom in an FCC. Are you clear with me on this? All right, very good. Now, it's the same structure for, what was the word? Zinc blend as well. But in zinc blend, what's going to happen? Each alternate atom would be of different shape, other type. Okay, I don't want you to visualize zinc blend right now. Don't worry about it. We'll get to that later on. Today, I just want you to know what is the diamond structure, because that's the structure for silicon. And that's the structure for 3,5 compound alloys. But in that case, we call it zinc blend, right? With me? All right. So, and there's another way. I'll skip over the right picture right now, but I'll just, because this is what I want to get to that. So the diamond structure here is shown. So ignore the black color for now. They all are white for now, right? I'll tell you then what is the special thing about those black atoms which are shown. So these are all white atoms shown. What they're showing now is they're showing the connections of atoms with their nearest atoms. So if I pick any atom, let's say, so okay, today you will, from the start of the lecture till now you understand that we start with sodium chloride and we say there are infinite number of sodium chloride in every direction, right? And you must be saying that just take a cube and you are okay there, because there are 8 atoms you have to deal with, right? Why have so much fuss on unit cell? Now you see why. Because silicon, or the material that's important to us, is not just that simple as like sodium chloride. So it has more atoms in it. All right. So if I pick one atom, say I pick this guy, this one, right? So it has to make 4 connections. Silicon is group 4, right? So outermost shell has 4 electrons and 4 empty states, 4 valence states. Sorry, I'm bringing your chemistry back in. Shells around atoms. How many electrons are there in the first shell around a nucleus?
2.
2. You guys remember your chemistry. How many are there in the second shell? It's okay, just say, you know the number. How many in the second shell?
2 again.
4.
Is it 4?
8. It's 8. How many in the third shell? Again, 8. It's okay if you don't remember. But you remember, if you take half of them out, that's group 4. So which means there are 4 electrons and 4 empty states. So now this atom which I put in red has to make bonds with 4 other atoms so it can satisfy those 4 conditions, right? So now each atom has now completely filled outermost shell, but we'll come to that later on. I just want to say, okay, this one silicon atom is making connection with 4 other silicon atoms, right? Now, those are his nearest neighbors. And if I were to just show you why it's nearest, this is the nearest one. This is too far away. This is too far away, right? So the nearest one are this, the one which are shown, and here also there is one connection shown. And this guy. Oh, not this one, sorry, this one, not just these 4. Now if I say, if I take step back, and I didn't take that step back, somebody else did, they say, okay, we see another smaller unit cell in this guy. We see another thing, that the half of the lattice constant shows us another thing which is symmetrically can be repeated over and over, and this can represent this thing. So interestingly, if we go a little bit back, we can find, am I missing any joint? I think I've put all the four, yeah, all of them. So we see another smaller unit cell, which can be taken to be repeated. You would not see that right now, but trust me on this one. There's another more simplified thing within that diamond cell. Okay, we will leave it at that. And let's see, there's one more thing I would like to touch upon before I can let you guys go. Now, if I know the volume of a unit cell, right? I know how many atoms are there. I can find the density of atoms in that cubic cell, in that unit cell, right? Why do we want to find density? Okay, why do we use density instead of actual numbers? Why do we use density instead of giving actual numbers, how many atoms are there?
You can scale it up.
It's easy to scale it up. It's easy to then calculate later on. So then you can find out exactly what's the dimension and you can just multiply it with that dimension, right? So scale it up. Like for example, universities likes to brag about, oh, our student teacher ratio is, oh man, how many are we here? 27, is 27 to 1 or 25 to 1, right? So they don't want to tell exactly how many students are there and how many professors are there, but just brag about. And then there will be another university that will say our student to teacher ratio is 15 to 1, right? Which one would you like, 15 to 1 or 25 to 1?
15 to 1.
Right? So we just show density so people can have a feeling, okay, how much attention each student will get. My goal is I would like to pay attention to each one of you, right? That's why I have your video on so I can take a look of what is, who's doing what. So in semiconductor also, we find density. So we can just give the density to people and then maybe they're using 2-inch wafer, maybe they're using 4-inch wafer, maybe they're using 16-inch wafer, right? Wafer size. You have just given density, wafer size, you buy whatever you want, and you can calculate your number of atoms, right? So let's do this exercise. Maybe you have done that already. Prashanto, you are with us?
Yes, Dr. Iqbal.
All right. So after class finish, we have to post these lectures on YouTube also. All right. So that's an example from the book. Calculate the volume density of silicon atoms, number of atoms per centimeter cube. There is a Q here. When you talk about volume density, it is always going to be per centimeter cube, right? But if somebody asks areal density, then you're talking about the area. Then it will be centimeters square. So then you will be looking at different things. So in terms of volume, you'll have to look at the whole volume, the whole encapsulated thing between these 6 walls, right? So the whole thing. But when you talk about the areal density, then you are just picking one wall and you are counting how many atoms are contributing in that one wall. Make sense? So different numbers, different counting, different way of looking at things. But they both are related at the end of the day. All right, so if I go back to this example, again, we can pick up the book and I can walk you through this example and possibly do this with you while we are going through and break it down for you. Let me get to that and then I'll share my book with you. Give me 5 seconds, I got it. All right, so for silicon, the lattice constant, okay, write it down somewhere big. Lattice constant for silicon, 5.43 angstrom. For effect, forever, you'll remember this number, 5.43 angstrom, right? Now, it says volume density, okay? So before we do volume, we can do areal density, that's easier. So I'd say, okay, we need a lattice constant, which means the front facade we can find out by multiplying the side with height, right? So for a cube areal density, this is lattice constant A, this is lattice constant A, and the depth is also A. That's why that's the lattice constant thing. So I take, okay, this is the area I'm using for my areal density, so that's what is here. Now, you see 10 restored minus 8, because density we always use in centimeters. Remember, another important thing to remember, when we talk about wafers or semiconductor materials, we will always talk about the density in per centimeter related units. So you have to go from angstroms to meters and then bring it back to centimeters. So what you end up is 10 raised to 1 minus 8, right? With me on this? Areal density. Now I have to go back and see how many atoms are there in that front facade, right? So for that, I have to turn my annotation on so I can go back and page up, go to that big, where is that big picture of, all right, here it is. And scroll slow, otherwise it just jumps. All right, so I have to look at this guy. So I take front facade. How many atoms are there in front facade? Can somebody help me count? So we are looking in just this front face. How many atoms are there in this front face? You can pick any face, by the way, because they're all are same. All right, how many atoms are in this front?
5.
5, okay. We got 5. You guys can chat also. So one person said 5. I read 5x1. Anybody else? The thing is, we have to look at contribution. So for this one, all right, Lara says 2. Anybody else? Anybody between 2 to 5? 3? It's given in the book, but let me break it down why we are doing this. So what is the, if I were to pick one, what is the contribution of, say, this atom to that square? What is the contribution of this atom to that square? Now we are talking 2D. So don't look at the sphere, look at it in 2D, that'd be a circle, right? What's the contribution to this side of things?
1/4.
1/4, all right. How many are there contributing 1/4? 4 of them. So we say 1/4 by 4. And then this thing right in the middle, because it's FCC, right? Which is contributing the full thing, right? So hence, we have what we have in there on that figure. Oh, sorry, in that example. Let me take it. So thus we have 1/4 times 1/4 plus 1. Does that make sense?
Sir, if we were trying to figure out the volume density, it would be 1/8, right?
We'll get to that. Just stay with me. We'll get to that. Then that one corner atom in my room, if you think about it, will be contributing 1/8 to it, to the volume. Yes, right. So now you have to be careful when you do this calculation. And trust me, we have exactly 6.8 times raised to power 14 atoms in 1 centimeter square in undoped silicon, what is given here, in 100 plane. If you pick another plane, then we have to do the calculation again, right? All right, fantastic. So now we go to the volume. Now, 8, let me go back to the picture, but let's we just look at the bottom first. So instead of doing the just the square, now we are doing the cube, right? We are looking at the volume. So same, convert it into centimeter and do the volume. But how many atoms are in that cube? Let's go back. Let's take a look. I'm walking you through. I know for some it may be very simple and straightforward, but for some it may not be. So let me just walk you through this, the whole thing. Now, I have to get contribution from different things. For me, what I would do, I would write down, I would say, okay, first I say corners. I say C. What's the contribution from corner atoms? What's the, okay. So let's pick this guy. So who said 1/8 of this is contributed to that volume? All right, Omar said, are you all agree with me? Now, if I look at this sphere and I see how much of it is inside that volume, 1/8, right? Okay, so I say corner one is giving 1/8. How many total are there on that, all the corners? How many? 8.
8.
So that's the contribution coming from the corners. Then I say, let's see how many atoms are there on the faces and how much of them is being contributed. So this is at one face, right? And if I look at the sphere, how much of it is inside the volume?
Half.
Half. All right. So one face, one is giving. And how many total are there on all the faces?
6.
6.
6. 6 of them. Very good. Very good. Now I say, okay, what should we call these guys? Let's call them blacks. I don't know what's a big word. How many blacks are there? They are all fully contained inside the volume, right? How many of them are there? 4. So what's the total number of atoms inside the cube? This is 1, this is 3. 4 plus 3 plus 1, 8 of them, right? So that's exactly what we are doing here. We said we have calculated the total number of atoms and divided with the volume. All right, you see that? So that's again a simple calculation, but you have to know where to look for the answers. So total 8, 8 divided by this guy, we have exactly 5 times 10 raised to 22 atoms of silicon in 1 centimeter cube for, now does the plane matter now? Does the plane matter? It doesn't matter because the plane was important because we had to know which plane to pick to find the areal density, right? But what matters is, and it will come later on, is if we have any doping done to that. But for silicon, that's the uh, volume density of silicon atoms. All right, questions? All right, if there are no questions, we are almost to the end what I wanted to accomplish today because there are more things. Okay, let me take you to the Blackboard page. So you have seen that, and I'm just going to show you what I'm planning there. Let me make sure I got the right thing up. Okay, this is my other screen. So I've started populating. Again, module 2 has been made available. I was listening to AC/DC, if you have seen behind my picture. Highway to Hell was playing. So, all right. So I've started. So I put a YouTube video. I'll put the live session, soft chalks. Everything else will come later on. They are not available, made available to you yet. The only thing has been made available is activity 2.1 so far. But you know the drill, right? So I hope you are following me now. How things happen when I keep rolling things out, and then I'll send you a message when things are out. All right? I hope we are together on how we are using technology for us. All right? Questions? All right. If there are no questions, I'll let you guys go. Stay healthy, stay safe, and I'll see you guys next week.
Okay. Thank you.
All right. Take care, guys. Bye-bye.
Hey, Professor.